decoherence, in adiabatic quantum computing, and quantum annealing. It summarizes work we've done with all of those. Many of them are here. I will, however, focus on work that we've done with Marius and Adrian. So I will talk a little bit about decoherence and measurement and their relation, and then look at how, by understanding and engineering decoherence, you could do flux measurement independent of bias point. And I will also touch upon why this is actually has been hard in the first place. And then I will give you an outlook on a poster that we have on cooling a structural environment and an update on randomization effects. So let's recall kind of basic notions of decoherence from the by now 70-year-old Bloch equation. If we're putting a qubit on the Bloch sphere, we typically can actually have three kind of decoherence channels. One is T2. So if, say, 0 and 1 is where our Hamiltonian is, then every motion on the equator corresponds to phase, and randomization of the phase is a pure T2 process. T1 is relaxation, which means if we are starting in a superposition of 0 and 1, we are going to change the probabilities of 0 and 1 ultimately towards thermal equilibrium. And then what is not shown here is that the environment always induces a change of the effective Hamiltonian, which in its simplest form would be a lamp shift. Now, if we connect this to measurement, let's review what we expect from textbook measurements. If we have complete pure dephasing, which means that we are starting from a pure state, we have our basis psi I of our Hamiltonian eigenstates, then pure dephasing means we're going into incoherent mixture, and the probabilities are predicted by Born's rule. If we do an ideal measurement with outcome I, then we are simply getting our density matrix into psi I. But if we are measuring and we are not recording the outcome, we're getting the exact same final state as in pure dephasing. So if we think about designing measurement, dephasing is our friend. We have to dephase. It's the ensemble average of wave function collapse. Now, dephasing has famously not solved the measurement problem. If you want to see two distinguished senior physicists taking their argument at the Institute of Advanced Studies into journals, I invite you to check out this paper. But understanding measurement in a decoherence language certainly has reduced kind of the mystery of the measurement problem. It at least helps us to disentangle what the real measurement problem is, the break of unitarity by observation. Part of the motivation for what I'm going to show now are ideas, for example, explained here, that if we have very strong measurement that we can do at any point during the anneal, we may have very powerful paradigms for quantum computing. Now, how are measurements usually done how would we like a measurement to be? We would like it to be detector dominated, which means that we have a weak system Hamiltonian and a measurement device and interaction that is so strong that we are always measuring in the basis and forced by the detector no matter what. And again, we want T2 processes because they dephase. We do not want T1 processes because they induce flips, so they falsify the result at the post-measurement state. We ideally learn in textbooks, when we learn about the measurement postulate in quantum mechanics in textbooks, nobody tells us about the working point of the qubit. So we want to do this independent of the working point. And saying that we don't want T1 is the same as saying we want to be quantum non-demolition. Which means in the orthodox definition, the first definition in the Baginski-Khalili textbook is a measurement that you can repeat with guarantee of the same result. Now, this is not usually how it's done in superconducting qubits, and the reason for this seems to be that in kind of atomic physics, typically, or optical physics, the detector is made out of a very different system than the measured objects, which typically has much larger energy scales. In quantum annealing with superconductors, we measure Josephson junctions with Josephson junctions. So we do not have an a priori strong separation of energy scales. So we typically have qubit-dominated measurements, which means that if we want to which we do because we want to have a good on-off ratio, and which can be made QND if the qubit Hamiltonian and the observable that we measure commute. Then we can still repeat it because then the qubit basis and the measurement basis are in fact the same. And this is an extremely powerful paradigm, but it does not allow you, for example, to do a flux measurement at anti-crossing because you're at the wrong working point. In other words, when I'm doing a sweep where I have flux eigenstates outside and superpositions in the middle, here in the middle, the Hamiltonian is not diagonal in the flux eigenbasis, so here I cannot measure flux. So we wonder, can we change that? We can only do flux measurements far outside the flux degeneracy point. Well, I wouldn't be standing here giving this talk if the answer wasn't yes. So if you want to measure the flux at any working point, we again want long T1, we want short T2, and ultimately this boils down to having switchable ultra-strong coupling. Ultra-strong coupling in this jargon means that the coupling scale is larger than the qubit energy scale. And what that really means is that, of course, because we want to be able to switch off the measurement, we need to specifically look for an enormously strong on-off ratio of coupling to the detector, because otherwise we're measuring all the time. If we just switch from ultra-strong to strong, then we still have unwanted decoherence. And we think it's reachable with a intermediary and with careful pre-measurement. So this is how the idea put into flux qubit language. We have a flux qubit, we have a double well, and we want to be able to measure flux with 50-50 probability, as the measurement postulate tells us here in the center. So the setup we propose has a flux qubit, and then an intermediary loop with a compound Josephson junction squid, and a readout squid that measures this loop, and another control bias line that allows us to switch on this intermediary element. And this is meant to be able to maximize on-off ratio, so there is no direct, ideally, no direct coupling between flux qubit and the squid, but we use this intermediary to get a strong on-off ratio. So here in the middle, we operate this with flux bias such that we can go from a situation where we have a low barrier, or in the extreme case, no barrier, when we don't measure, to having a barrier in this loop by essentially tuning the compound Josephson junction. And the fact that this is possible has been shown in gate-based quantum computing in this paper from the Ustinov group. To put this in Hamiltonian, we have our coupling Hamiltonian. We can here change the Josephson coupling. If it's switched off, we have a pure parabola. If this is switched on, we have a double well potential. And this is then coupled to the loop of the qubit, and this flux in here can be read out. So the measurement protocol has 4 steps: initialization, pre-measurement, effective decoupling, and readout. Initialization means we are making our superposition that we would like to measure, and we keep the coupler in a single well regime, so it's just a harmonic oscillator, it's being dragged along, it gives a bit of lamp shift, but this lamp shift can be kept small, and we are basically decoupled. Then we do a pre-measurement, which means we are now ramping up the barrier in the coupler, and by this essentially pull out this initial blob of probability in the coupler into a left and right, so it has essentially no overlap anymore. So we are creating, if you want, a Schrödinger's cat state, a photonic Schrödinger's cat state in the coupler, and by this pre-measure the system. And what this does is, these are pointer states in the sense of measurement theory, and because they are so far away, now for the qubit to switch, to make an error between up and down, it would actually have to drag Schrödinger's cat between its both states, and if the overlap is small, that would be exponentially unlikely. So in the language of, so this is effectively done by ramping up the middle. So in the language of decoherence theory, you're creating a non-perturbative lamp shift that essentially suppresses tunneling. So in a way, even though your Hamiltonian still has a tunneling term, while you're measuring, your effective Hamiltonian does not have it anymore. So this is freezing qubit dynamics, and then you have time to essentially read out the pointer with a squid, and that gives you the right probability. So increasing the tunneling, and a lot of the preparation for the measurement happens while you ramp up in a still fully unitary way, and then you're observing your pointer, and only then you break non-unitary. You break unitarity. So again, this is the protocol summarized. And if we go through parameters, we see that we really need ultra-strong coupling. Otherwise, the pointers are not well separated, and we won't get this effect. But if we do so, we can in principle get almost close to QED measurements with relatively realistic parameters, which means the risk of misidentification in the second measurement is essentially 0.4%. And we have a preprint on this. At the same time, of course, measurement-induced dephasing happens, so you go down from 50-50 superposition into one of the two states. So this also means that the ramping up of the barrier in the middle needs to be non-adiabatic on the scale of the qubit, so that is a bit of a tall order, because otherwise you would falsify your states, and you're working with a coupling loop that you would probably make out of niobium, and it will make with relatively high Josephson energies, so you get a bit of separation of timescales. This, I think, should be possible to run as a proof of principle, and then there's a whole different question whether this can run in a large setup. So let me, in the last few minutes that I think I still have, just highlight two more aspects where thinking about decoherence in a little bit out of the box way can probably help you. One is the idea of environment engineering. So the idea here is that if we have our rugged optimization landscape, then our mantra is typically that if we only go down in energy, if everything is classical, we get stuck in local minima, so we have to heat again, we have to do classical simulated annealing, takes an exponentially long time. If we have pure quantum annealing, if our system is fully coherent, we will be able to liberate ourselves out of these local extrema. However, if we are fully coherent, energy is conserved, so we are actually not improving anymore. So throwing on a little bit of relaxation could be helpful. And the idea is that we essentially selectively relax high energy portions of the state, very much like an evaporative cooling. And if you don't know what evaporative cooling is, it's like blowing your teacup, where you do the same thing. You take the high energy portion of your tea, which is in the vapor phase, you put it away, the system re-equilibrates, and you have an effectively low temperature. And this can be done by putting a whole cold heat bath to sigma x, not to sigma z, so to the coupling loop. But all the details of this will be highlighted in a talk by my graduate student Peter Schumacher later this week. I believe it was Tuesday or Wednesday. The test circuit that you would use to make this would couple a cold heat bath in the form of a coplanar waveguide to a coupling loop. And here are several plots that show you some improvement, but yeah, this is Peter's talk. So in the last minute or so, let me give you a small update and context towards what was essentially my last year's AQC talk, which has to do with the dissipative phase diagram. So historically, we know that if we damp a single qubit really, really strongly, if we take the dimensionless damping to order unity, which means that the quality factor of coherent oscillations would be 1, so you're critically damped, you do get a dissipative phase transition that was predicted by Leggett in the 80s and realized in one experiment, in a brute force experiment in Finland in the late 90s, and in a beautiful experiment in Waterloo a couple of years ago. So we have taken this to the situation where we have also a lot of qubits with k local couplers and essentially n qubits. So the phase diagram there looks as follows. Here are typical damping strengths, and if everything is weak, then we just have roughly the same Hamiltonian as originally. If the damping is really strong, we have completely classical physics. But there's an important regime where your damping strength is such that no single or 2-qubit coupling gets strongly renormalized. But the very fact that you have 1,000 qubits, you are essentially decohering your ground state, in quotes. Now, decohering your ground state is a dangerous statement to say because it seems to violate thermodynamics. But this system is not thermodynamic in the sense that every qubit brings in its own heat bath. So as we're putting in more qubits, we're putting in more noise. So the lesson for this is that if we have a 1,000-qubit quantum annealer and we want to explore its full state space, the quality factor of its qubit operated in the gate model needs to be at least 1,000. Otherwise, we're losing entanglement. And this is even though 1 over 1,000 damping seems to be very, very low. And this is, again, in this preprint. And again, this regime can be mapped by single qubit dephasing. So you take your initial state and you run it through single qubit dephasing channels where the survival probability is being set by this damping factor. So again, this was mostly just this AQC talk, but I wanted to share this phase diagram that we have and also put this into context because this is another consequence of environment-induced renormalization that is usually not captured in T1 and T2. So I think that I tried to motivate that we need to take the basis dependence of decoherence seriously. Decoherence is typically naively modeled in the qubit eigenbasis, but if you're changing the qubit eigenbasis a lot along an annealing schedule, that needs to be reconsidered. I showed you that if the environment strongly renormalizes your qubit, it can actually be good because it allows you to measure independent of working points. And then I highlighted very briefly 2 new results that we can talk about later that also have to do with decoherence being put to use. Thank you very much for your attention.
Thank you. So regarding the interaction with the environment, what are the prospects of including other environmental models and kind of getting closer to the physics and all the details of superconducting devices?
So for the renormalization effect, it's on our agenda to study the same setup with 1 over F noise by essentially coupling the system to a bunch of 2-level fluctuators. For the structured environments, we want an environment that is high frequency dominated, otherwise it wouldn't work. So this will always compete with dephasing, and where the detector just goes on top.
First, thank you for the lectures. It was very interesting. And I have a question about the decoherence. Does it have to be quantum, in a sense? Because in the sense that can you distinguish between entanglement and the cases of just wave dynamics?
So for the pre-measurement scenario, that is definitely a consequence of entanglement with the environment. And so is the renormalization scenario. And I think any of these type of renormalization effects, because they're essentially, I think they are a direct consequence of entanglement. I would say that classical noise, where entanglement plays a subordinate role, would mostly appear in 1 over F type scenarios. You could argue, and this is probably something for the coffee break, whether there actually could ever be decoherence without entanglement of the environment. Only that sometimes describing the entanglement with the environment is not a convenient way to write it down. Even if you have a totally classical noise source, nobody forbids you to write down a Hamiltonian model for it. And then if you assume that all noise sources can be modeled by a Hamiltonian, then I think you do not get decoherence without entanglement. However, oftentimes the mathematical instruments that you use to describe it, say when you derive a recoupling master equation, doesn't highlight the entanglement aspect.